Welcome everyone. It's a great pleasure to have José Luis Bernal here today. Thanks a lot for accepting our invitation. José is a Ramon and Cajal Fellow at Cantabrian Institute of Physics, while he did his PhD at the University of Barcelona before becoming a Davis Postdoctoral Fellow at Johns Hopkins University. José's interests are in cosmological tensions, dark matter models, and line intensity mapping. Today, he will present current status of line intensity mapping and promises for the future. José, please, you can start when you're ready.
Okay, thank you, Leonora, for the invitation for being here and also for the introduction, and also thank you everyone for connecting to the talk. I'm aware that this is a topic that is slightly off from the current topic, the usual topics that are discussed in the CosmoVerse seminar series. But I'm going to try to keep connecting all the time the potential that line intensity mapping may have to test models beyond lambda cold dark matter that can be very interesting to potentially solve the cosmological tensions that are currently between some of the observables and experiments. So I'm going to introduce a bit the line intensity mapping as an observational technique and the different experiments that they have and why this can be that promising to test the universe in different regimes that are beyond the reach and capabilities of other more traditional cosmological observables or observational techniques. And I'm going to do this in a pedagogical way because I'm guess that the audience today can be quite diverse. And then I'm going to dedicate also a big chunk of the talk to the main elephant of the room all the time for line intensity mapping, that is dealing with the foregrounds. I will do this more for the galactic foregrounds, as it would be the case, for example, of 21 centimeter line for the Mir with like a big focus on the Mir class observations. But also going to discuss line interloper contamination, which is important for emission lines at higher frequencies. And then if I have time left, I'm going to also discuss the potential contribution of the CO line emission in the CMB observations, specifically for the CIB maps from CMB experiments, and how that may contaminate the signal and also be an opportunity to detect this contribution from the large scale structure with these experiments. At all times, I also wanted to keep in mind that line intensity mapping is still a very infant field, so we can't compare it right away, its current capabilities with all the potential and all the power that other observables of the large scale structure, like for example, galaxy clustering or weak lensing, already have, because there have been a lot of work and dedication, both in theory and in the observations on those fields, and we're still working on that path for line intensity mapping. Okay. So first of all, let me begin with the definition of what is line intensity mapping, and we can go there directly from the three words of its name. First of all, we use the word intensity mapping here because what this technique does is use the whole integrated signal without requiring any detection threshold, as for example, it could be the case for galaxy surveys that require that a point source is detected above, like, I don't know, something like 5 sigma or 10 sigma over the noise to be counted as a galactic detection or similar. In this case, the information from all incoming photos along the line of sight is taken, and therefore will collect information from all galaxies and the intergalactic medium along the line of sight. But that will give us only a two-dimensional information because of this integration of all the radiation on the line of sight, and this is why line plays a role. And this is because by doing different treatment of the signal and the spectra of the observation on the line of sight, what this observational technique attempts to do is target identifiable spectral lines, be it in absorption or in detection, in order to isolate it from the continuum emission, and therefore, since we know the rest frame frequency of those lines, we know the redshift that each part of the radiation in the forms of emission lines or absorption lines we are detecting, and we know this because we can tune the observed frequency of our detector, always that we have good spectral resolution, and that's a requirement for this kind of experiments in the experimental side, in the instrumental side. And this way we can build three-dimensional maps because we will know where along the line of sight each of the radiation may come from. And this would be, for example, a couple of examples of the spectra that we can expect from a given galaxy and the lines that we would be detected. This is for, where I hope that you can see my cursor. This is for the infrared lines, specifically the C2 line, which is the brightest line in the infrared, but also all the CO rotational lines ladder, and also on the optical. And as I was saying, what is attempted is basically remove this continuum and isolate these emission lines from its source. I'm not including here 21 centimeters because basically that could be a very isolated line on the over the radio continuum. Okay, so let me now use a comparison of how a galaxy survey would work compared with intensity mapping. This is from a slice in a simulation. This is a 1 square degree around redshift 5. The width of this slice is 0.2 in redshift. And here, each yellow dot is basically every halo in the simulation. And if we apply a somewhat arbitrary cut here, but this is just for illustration, on the stellar mass for the galaxies in order to basically account for which of these galaxies will be detected or not, this is what we will be left with. You can still do a statistic with it, but we are missing many sources, and also some of the features of the large scale structure may be lost in all these voids that are basically due to not detecting any galaxy on those. On the contrary, for resolutions that are characteristic at these frequencies for CO experiments and C2 experiments, this would be how we would observe, or how the cosmological signal would be on this field. This is neglecting any contamination from the noise or the foreground. So this is very idealistic. But here, this is how you will see. You will be basically trading off any information at very small scales, because basically what line intensity mapping does is use low aperture telescopes, because we don't need those high significant detections. But we will be receiving, for example, here in these points, all the faint emission from the faint galaxies that we wouldn't detect otherwise. And basically what we are targeting at the end of the day is to measure the intensity fluctuations. And of course, since this radiation comes from galaxies, especially at low redshift, we will be tracing the matter density fluctuations, and the signal, the amplitude of these intensity fluctuations could depend not only on the amount of matter, on the amount of galaxies that we have, that will be the tracer of the large scale structure, but also on the specific line luminosity for each galaxy. And this is why line intensity mapping is also a proxy for extragalactic astrophysics, because it depends on all those astrophysical processes that trigger the emission line. Therefore, line intensity mapping has information both for cosmology and astrophysics. I assume that for all the folks gathered here today, it's going to be more interesting in the part of the cosmology, so I'm going to be focusing on that. But in general, for cosmology, we can understand line intensity mapping products as a noisy map of all the galaxies and intergalactic medium. In contrast, what a galaxy survey could give you, that is a detailed map of the brightest objects. In the case of astrophysics, instead of giving you a very detailed picture of the high luminosity end of the luminosity function, it will give you the aggregate of all the meters and diffusion emission in such a way that you can do integrated population studies. So, in order to go from a first principles point of view to the final signal, you would have to start with the matter power spectrum, then account for a galaxy bias, and then for all the astrophysical processes in order to reach the final line intensity fluctuations. And all these properties make that intrinsically there are three main features that make line intensity mapping unique with respect to other probes of the large scale structure. First of all, as I already mentioned a couple of times, it captures the faint emission, the emission from faint and diffuse sources. And this also grants access beyond the reach of galaxy surveys, because since we don't need the high significant detections, we can reach those redshifts for which galaxies are already too faint and also too sparse to have enough numbers to do cosmology with them. Finally, again, since it does not require this detection of each individual source, we can use low aperture telescopes and quickly map very large three-dimensional volumes on the sky in such a way that this was a study for the SNOMAS call for papers led by Kirit Karkare, and if I recall correctly, it would be around 2 orders of magnitude cheaper to do a line intensity mapping survey with the same capabilities of a galaxy survey. Of course, accounting in the idealistic case that we can control some of the challenges that I'm going to discuss later. And then, as a teaser from some of the things that I'm going to discuss later, these three main features from line intensity mapping make that it's very powerful to constrain new physics that may change some of the following things. Since it has this huge range of going very far in redshift and also tomographically, because you can control which redshift you are acting, basically anything that changes the matter power spectrum in a scale and time independent way, as for example would be massive neutrinos, you can attempt to constrain it with line intensity mapping by basically doing tomographical measurements. Also, anything that changes the luminosity function, that can be a change to the halo mass function, or anything that changes the astrophysical processes that trigger the line emission, would be detectable in the line intensity mapping summary statistics. You could also detect new signals, for example, I don't know, things that would will produce a very narrow spectral energy distribution, as for example dark matter decays, or if there's not a lot of cascades, even dark matter annihilation may have some signals there. Oh, and also, since we can map very large three-dimensional volumes, in the case, and this is a big if, we can deal with the foregrounds at very large scales, we will be able also to probe the ultra large scales, maybe in a better way than with galaxy surveys. But with this last one, I'm a bit more skeptical than with the others. Now, I also want to clarify here that I'm going to be focusing mostly on the line intensity mapping of any line in general, but always after reionization, because most of what I've already said, but what I'm going to be saying later, both for the signal, the capabilities, the sensitivity to models beyond the lambda cold dark matter, and also the way to model it, is going to be very different for the 21 centimeter emission from cosmic dawn and reionization. That is has a very rich phenomenology for almost any model beyond lambda cold dark matter, but I'm not going to be focusing on that because I work mostly on the other. But I'm happy to answer any question within my capabilities after the talk. Okay. So I'm going to be going through some of these now. This is an example of how can impact the constraints on the luminosity function for the effect that we are obtaining all the photons along the line of sight. And this is an example for the time collaboration in 2021 led by Watch Our Sun, that these are detections of the luminosity function, and this would be some limit in the detectability due to these sources being too faint. And we don't know, and there's a lot of interesting things that we can learn about astrophysics and cosmology on this end of the luminosity function for this slope. Of course, how important all this signal is going to be on the aggregate intensity fluctuations is going to depend on this slope. But this is also why, with time, we would be able to obtain constraints, but for an extended time that will have a factor 12 in sensitivity, we will be able to constrain the luminosity function very precisely, as you can see in this plot. Okay, we have a pretty clear picture of what is the evolution of the universe and how perturbation grow, especially for lambda cold dark matter. And this is basically based on observations that we have on two very specific moments of the evolution of the universe. First of all, we have very good information of how was the universe at recombination, thanks to the observations of the CMB, especially through the primary anisotropies. And then we have some information about how perturbations have grown, but only in an integrated way through the CMB secondary anisotropies, such as, for example, lensing or the Sonia-Seldovich effects and so on. But also, most of that signal peaks around redshift 2 and below. So that these are signals that, epochs in the evolution of the universe that are already also constrained and probed by galaxy survey. However, we don't have any direct probe of anything that happens in between, and there may be deviations from the standard evolution of the universe that take place at these epochs that would be very hard to probe otherwise. And this is how line intensity mapping, thanks to the reach at high redshift, can help complement these two very powerful observables, as for example Galaxy Service and CMB. Also, this way, it could extend all these tomographic studies that I was mentioning before towards much higher redshifts than with Galaxy Surveys. And this brings me to discuss the current state of the experimental and instrumental landscape for line intensity mapping. And here I'm showing all the ongoing and funded experiment, or at least most of them, for line intensity mapping in a plot in which I'm discussing the redshift that will be probed in the x-axis. In the y-axis is the solid angle on the sky that is going to be covered and probed by these experiments, and the color of the line of the lines is which spectral line is targeted, whether it's running and funded, instead if it's solid or dust, and also the width of the line is the line interlopers or the main target line that it will be tested. So as you can see, we will be able to test and probe very wide ranges in redshift with different lines. Here I'm showing the main lines in the infrared, such as CO and C+, the main lines in the optical, which would be Lyman alpha and H alpha, with O2 and O3 as their main interlopers, and also, of course, 21 centimeter in the radio. And as you can see, all of them are very narrow fields on the sky. And this is basically because, as I said before, we are currently in a Pathfinder stage for all the technology that is involved for doing line intensity mapping. However, you also can see here that we will be using emission that from the radio to the optical, and that's basically a very different set of systematics from the instrumental point of view and also the observational point of view. So that's very good in order to cross-correlate the signal and do complementary studies in the way that line intensity mapping is intrinsically multi-tracer, because you would be able to probe the same structures with different emission lines, which also will give us access to all kind of different astrophysical processes and phases in the galaxy morphology and galaxy evolution. So this is very promising and very powerful for astrophysics and cosmology, because thanks to this, we will be able to cross-check all the systematics and also reduce the cosmic variance. And the good thing is that we already have, even in this Pathfinder stage, some detections. Almost all of them, if I'm correct, are in cross correlation with galaxies, and some of these detections are for Meerkat. I'm going to discuss this detection in cross correlation with galaxies. There's also a claim, as far as I know, they still haven't been published, of detection in the auto power spectrum doing interferometry. Also with head-decks, with the Lyman alpha doing stacking. COPS is the only detection in the auto power spectrum, if I recall correctly, but this is at very, very small scales. So this is very hard to interpret for cosmology. And also we have the detection in mind. There are some other detections that are not in this plot. Chime in cross correlation with galaxies too, using the products of Planck to cross correlate with galaxy and quasars in order to obtain detections that can be interpreted as the signal from C plus or CO32. Also 21 centimeter in cross correlation with galaxies from the Green Barrel telescope. So there's already a lot of success in the experimental side, and we are steadily building towards basically setting the path to huge facilities as it could be, for example, the SKA observatory. Of course, being able to probe this huge range of redshift could give us, as I was saying, access to this very high redshift universe. So basically, the first thing that we could do would be try to measure the baryon acoustic oscillations at this redshift. And this is some forecast that I did back in 2019 for the BAO precision that we may have with some of these experiments, and also futuristic iterations of them at high redshift. This is focused on lines related with star formation rates. But as you can see, we would be able to extend the current, and this is our forecast, that the current reach by a galaxy survey, for example, as DESI towards much higher redshift, and this would be great to probe potential deviations of the cosmological constant at higher redshift. You can even extend this to much higher redshift using the velocity acoustic oscillation proposed by Julián Muñoz with experiments like HIRA. But this again will be a bridge between galaxy surveys and CMB experiments. As I was saying, being able to probe the growth of a structure tomographically and access a huge range of huge volumes in a cheaper way would grant access to probe, first of all, neutrino physics, because we know that massive neutrinos suppress the clustering of matter in a scale-dependent way, but the scale in which this suppression happens is the free streaming scale that changes with redshift. So it has a very clear signature in the growth of a structure with redshift and in the power spectrum. So we can be able to detect that for neutrino physics, or in general any non-cold dark matter that may affect the growth of a structure, as for example could be some warm dark matter, but also ultralight actions, as was studied by Bauer and collaborators back in 2020. Dark energy and modified gravity, I already mentioned it in the case of the BAO, but also through the effect that it may have in the power spectrum in a redshift-dependent way and scale-dependent way. This was as the case of the neutrino physics studied in papers led by Asadeh Moradinesa, this guy. And also, thanks to the access to those huge scales, we will be able also to probe primordial non-Gaussianity. And here you have some examples. This is for the case of neutrino physics, combining line intensity mapping with Planck constraints. This is for line intensity mapping experiments in the infrared. And this is results from a paper led by Gabriela Satopolito in 2021, breaking the analysis between primordial non-Gaussianity of the local type, FNL local, and compensated isocurvature perturbations between dark matter and baryons, basically by probing the different evolution of these two effects that have the same scale dependence, but the regressive evolution is different, combining the power spectrum for line intensity mapping with the kinematic Sunya-Seldovich measurements. Okay. But I'm talking about all the things that can be done, but not how to obtain that information. And basically, this is very important because we are cosmologists, right? The first thing that we do is try to compute a power spectrum. And in the most naive case, this could be for the temperature perturbations or the intensity fluctuations in the linear regime. The matter power spectrum times the square of the mean of the temperature times some factor that depends on the square of the second moment, of the luminosity function. The problem is that this has many limitations. First of all, the power spectrum is a Gaussian quantity, and intensity maps are very, very non-Gaussian because on top of all the non-Gaussianities produced by the gravitational collapse of the large-scale structure, you have all those astrophysical processes, right? So there's a lot of information that is beyond the access of power spectrum. And also the power spectrum, as you can see, only access to the first and the second moments of the luminosity function in a complete degeneracy with whatever may happen with cosmology. So things are very complicated. Therefore, due to this degeneracy, it will be great to be able to break this degeneracy with alternative summary statistics, as it would be the case of the Boxian intensity distribution, that is basically a proxy for the probability distribution function of measuring a given temperature in a given voxel, and this is a proxy of the full luminosity function. And this is because you can understand this probability as the sum of probabilities of having n emitters in a given voxel, which is a three-dimensional pixel, times the conditional probability of having a given temperature with those number of emitters in that voxel. And this Pn of t is basically subsequent convolutions of the luminosity function. Now, the BID is more prone to be contaminated by foregrounds, being a one-point statistic rather than a two-point statistic that is the power spectrum. But there are already a lot of or at least some proposals to deal with these systematics, as it could be the conditional Gaussian intensity distribution or the deconvolved density estimator, and especially particularly Dong Chung and other folks at COMAP are doing these studies. As a rule of thumb, the power spectrum is the best for cosmology because it depends on the integrals of the luminosity function, while the BID is the best for astrophysics because it depends on the integrals of the clustering. However, we can always combine the two of them because the combination is going to break these degeneracies. And you can see here from Ile and collaborators in 2019, the constraints on the luminosity function from either only the power spectrum, only the BID, the combination of two, and this is the relative gain in the precision. And as you can see, we will be improving quite a lot the precision by doing this combination. We can do this combination already analytically because this work was in a simulation-based study, but in a paper led by Gabriela Satopolito, we derived the analytical covariance between these two summary statistics that depends on the integrated by spectrum, and we showed recently, last year, in a paper led by Vivian Sabla, how the break of these degeneracies is great to improve the sensitivity for beyond lambda cold dark matter models. We did that for a general cut in the power spectrum, mimicking some non-cold dark matter, for action, ultralight action, and also for FNL. And we found for experiments like COMAP that we will be improving quite a lot by a big factor the sensitivity to these parameters. Okay, time is passing a bit faster than I thought. I'm going to discuss a bit how to deal with the foregrounds. Because, yes, intensity mapping reaches further, collects all the emission, but that also means that collects all the garbage along the line of sight that we are not that interested in. And that for us is mainly three different things beyond our target emission. First of all, we're going to have a stragalactic continuum emission that we need to remove in order to be left only with emission lines that we are interested in. This seems problematic, but with a simple treatment of the signal and PCA, since the continuum emission is very smooth, it has been shown that can be dealt with efficiently. Galactic foregrounds, especially for the 21 centimeters, is very problematic because the ratio between the contamination and the signal is huge. It's very many orders of magnitude. So we need to know very, very well and characterize very well the foregrounds in order to be able to not bias the signal. And then, as I mentioned before, there are interlopers that are other emission lines that redshift into the same observed frequency that we are collecting in the detector. Okay, So let me start for galactic foregrounds for this one case. This is probably the one that you are more related with. And this is some example from simulations from Isabella Carucci in 2020. And this is the main, the signal, the brightness temperature of each contribution from the for the foregrounds corresponding with the signal. So in this case, the instrumental noise is actually quite smaller than the signal that we're interested in. That's great. But these are the galactic foregrounds that are 3-4 orders of magnitude above the signal that we are looking for. And this is why, as I was saying, we need to know the foregrounds to the 0.1 or 0.01% level in order to be able to remove them without affecting this signal here. And however, if this was not enough, some of these instruments, as is for example the case of Meerkat, has polarization leakage at this very small signal regime. And that could be the signal from this dash dotted pink line, which is very difficult to characterize and to disentangle from the signal. So here we can do, the only thing that we can do is do a statistical analysis and try to remove it with blind methods, in order, such as for example a PCA, in order to be able to remove this contamination to the level of precision that we are required in order to be left with the signal. If we do this in simulations, all the foregrounds in simulations are very smooth, so we can remove very few modes with the PCA, and that could be great because that basically doesn't affect the signal, but real life is not as easy, and we are seeing in mid-class that we need to reconstruct all the signal loss that we have from the signal of interest that we have due to this foreground subtraction. Okay, so let me introduce Mirclass. Mirclass is a small collaboration that is using the Meerkat telescope in the single disk mode in order to perform a line intensity mapping survey of the H1 line. We have observations in the L band, and these are the detections that we have, around 100 hours observed. And we are currently taking observations in the UHF band with a proposal for getting up to 10,000 square degrees, and this is currently the part of the sky that we have been measuring with this UHF signal, but we plan to target these two red squares. And this is the detection that we had, cross-correlating the 21 centimeter signal with Wiggle C. This is I forgot, I don't have it here, but this is around, like, I think it's like a 5-ish sigma detection. The great thing is that here, 4.8. It was the first large scale detection of H1 in a very narrow redshift range between 0.4 and 0.446 and 200 square degrees. This narrow redshift range is because of the small overlap with the Wiggle C galaxies and having to remove out of channels from our observations due to radio frequency interference. But you can see that even with only 10.5 hours of observation, we have a very good detection here. The foregrounds were removed using PCAs, removing up to 30 modes. So you can imagine that a lot of information was removed, and we recovered it using a transfer function. That I can discuss later how it's used. It's basically calibrated with simulations and the actual foregrounds that we have from the observations. And it was confirmed with further detections. First of all, with a subsequent analysis doing different cleaning of this band, but also cross-correlating the mid-class observation with the gamma galaxies with an improvement in calibration and better observations that allowed that to only remove 10 modes instead of 30. And it was the same amount of omega H1 that we detected. So the question now is here if whether we can do better than do this blind PCA and remove all these modes and therefore have to reconstruct it with a transfer function. And the answer is yes, hopefully and thankfully, because PCA is very sensitive to the outliers. So if we take a more uniform footprint, even if we lose a lot of solid angle on the sky, it's going to be much better for the PCA. And all the discussion that I'm going to be showing now is in this paper by the middle-class collaboration led by Isabella Carucci in 2024. And from the initial map, that is the color map here, observed by by middle-class, and the pink rectangle, that is the Wiggle C footprint, we were left with the cyan and then also some window function. I don't remember now the specific word. So basically cutting or suppressing a bit the edges in order to downgrade their weight and have a more uniform footprint. And we saw that this would produce a much more smooth and stable PCA results. Furthermore, what we did here would be a mixed PCA that basically we separated and decomposed the initial map into two maps. One that was basically keeping the information on the large scales, and another one keeping the information in the smaller scales. As you can see, this would be the two maps compared with this one. Clean independently the two data cubes with two independent PCA analyses, and then mix them later. And we saw that removing only 4 modes from the large scale map and 8 modes from the small scale map, we were able to basically clean over foregrounds and obtain results for the power spectrum that were optimal for the chi-square and the fit-to-wear analysis, and also stable against different cuts in scales. The good thing is that even without any transfer function, because we saw that the transfer function was already always consistent with 1, we obtain a higher significance detection. And this also gives us the hope and the intuition that we may be ready for the autocorrelation experiments. And actually, we're pretty close. Doing internal cross-correlation, basically by cross-correlating signals from different antennas and also different time checks, we think that we are close to find this detection in the autocorrelation, clean of contamination, and this is a project led by Matilde Barberis-Corotti. Okay, I've been focusing so far a lot on the on the galactic foregrounds, but for higher frequency, we have also the line interlopers that, as I said, are other emission lines from different cosmological volumes that redshift into the same observational line, and it can be even brighter than the one that we are looking at. So, for example, we saw that the C plus line was the brightest line in the infrared, but if you want to do, I don't know, redshift 6 or C plus observations, you have the contaminations at very low redshift from the CO rotational lines. Similarly, if you want to do high redshift CO32, you will have the contaminations from this. And this may be a problem because, as you can imagine, since it could be mistaking the redshift of this signal as the redshift that we are here in the target, this could introduce a huge projection effect on when we pass from angles and redshift to three-dimensional quantities in order to compute the power spectra. You can see here in this example in which I'm targeting C plus at redshift 5 and I have contamination from the CO lines at different redshifts. This could be the map for C plus only. When you include all the lines, it looks a bit uglier. And this is how the measurements for the power spectrum, monopole, quadrupole, and the histogram of temperatures per voxel look like. So we need to account for this contamination. Otherwise, all our conclusions are going to be biased. We can do this in different ways. We can mask, either targeted or blind. Targeted would be using information from other galaxy surveys to infer what would be the brightest contamination. We can model the projection effects directly, but at some point, the uncertainties and having more and more parameters are going to also limit our inference for the information that we would be interested in. We can use spectral templates and deproject at pixel level, or use in a similar way than this modeling that I was mentioning before, cross-frequency angular power spectra in an analysis that would account for all this contribution along the line of sight and these projection effects between different multiples and scales. However, I've been considering all the time astrophysical line interlopers, but as I was saying before, if dark matter or neutrino decays, those are new in emission lines that could be observed as interlopers. So we can use some of these strategies to look for them. And this is something that I studied back in 2021. This would be the case of action decays. And especially for the multi-electron volt signal in the optical, it could be very competitive with current constraints. But also for the standard neutrino decays, if there are some beyond the standard model quantities, this decay may be excited and enhanced with respect to the standard model prediction. And we also saw that with things like CO map or future experiments using the intensity mapping in the infrared, we would be able to obtain cosmological constraints that would be competitive and complementary with experiments on ground and also astrophysical probes, as for example, the observing the tip of the red giant branch for the stellar evolution. Okay, I want to discuss very briefly another way to null the interlopers. That would be basically taking the same thing that is done for CMBD lensing. Basically, because we want to do the same thing. We want to remove some low contribution to the our kernel along the line of sight, and we can use external large-scale structure information in order to apply a cleaning filter of our map and statistically reduce the contribution from this low redshift. So the only thing that we will need to do this would be having overlapping galaxy surveys, and we have that by design because since we have right now pathfinders are built in order to have this overlap. And also we have basically the whole sky now covered by galaxy surveys at low redshift. So if we model our fluctuations in the intensity as the interloper, the target, and the noise, we can always have a map that is filtered by some external fluctuation on the large scale structure. For example, the galaxy number of the overdensity, and minimize the variance of this filter map. This would be model independent, and we can predict very well, and we have validated this with simulations, that what would be the signal of that final map. That could be basically the one of the target minus the one of the, and like basically as we increase the correlation between that large scale structure and the interloper fluctuations, we basically would be able to almost remove completely that contamination. As I said, we check that with simulations, and also we saw that we would be able to boost the signal to noise of our target line quite a lot, up to a factor 6 for the autocorrelation. If we have good cross correlation coefficients between the galaxies and the target line, and of course, this would also reduce the covariance for our observations. So this would be great. I'm running a bit fast because I'm running a bit late, so I'm not going to talk about this project that I did with Nicholas Cochran and Joe Dangley last year. Basically, as a single teacher, discussed that we are very likely detecting the CO line or contribution from the CO line with the CMB, and when doing component separation, there might be a contamination of this emission when separating CIB and the KSC, for example, and especially for template-based analysis, as for example the one on SPT, there might be contributions from the CO, both in auto and in cross correlation with the CIB, that may be biasing and we're estimating the detection that we think that we have of the kinematic Schneider date effect. If you have any question about this, we can talk about it later in the questions, or you can drop me an email. But I'm going to run to the conclusions in order to finish somewhat in time. I hope that I have convinced you that even if we are in a very infant stage of line intensity mapping, and that there are many challenges ahead, line intensity mapping has the potential to become a key pillar for cosmology and astrophysics, especially to constrain physics beyond lambda cold dark matter, because it will be able to capture the faint and diffuse sources and therefore somewhat probing the faint end of the luminosity function, which is usually related with the light end of the halo mass function. And this way, we also be able to access and reach regimes that are beyond the access of galaxy surveys, because we will be able to access higher redshifts or these smaller masses, or galaxies that are not probed by the galaxy surveys because they're too faint, or even quickly map large three-dimensional volumes. However, there are the analyses with astrophysics, and line intensity maps are very, very non-Gaussian, so I always advocate to go beyond the power spectrum, and some of my work has shown that combining the power spectrum and the BAD is make possible to break these analyses and also probe some of the non-Gaussianity in the maps, and therefore improve quite a lot the constraints, especially for beyond lambda cold dark matter. Foregrounds are going to be the main showstopper, so we need to work a lot quite on them. It seems that mixed PCA and homogenizing the footprint and the map work very well with continuum foregrounds, and those that are especially for galactic foregrounds. And for interlopers, we have several and very complementary approaches to deal with them, so I will advocate also for combine these different approaches in order to clean the signal as best as possible. We have several detections already, so I'm very close to the auto. So please be tuned, because I hope that in at least, let's say, this year, we may have some very good news regarding this. I hope. Don't quote me on that, just in case. And as I said, I didn't have time to discuss it in detail, but I think that we may be having contributions from intensity mapping of CO and maybe C+ also in CMB observations. These are very hard to model, but may impact the component separation that we have right now for CMB experiments, and biasing some of the conclusions that we are having for all of that. So this is all from me so far, and I'm open to any question that you may have. Thank you very much.
Thank you. Thank you for the great talk. Any questions? Susanna.
Hello, thanks a lot for the great talk. I have a very general question about the possibility of this line intensity mapping to measure the deviations, to measuring new physics. And the question would be why this line intensity mapping would give us more information than current observation that have less problems with the foregrounds.
Yes, that's a very fair question. If we want to probe the same regimes or the same volumes that have already been probed with galaxy surveys, line intensity mapping is not going to add anything. It's going to have always less signal to noise, because it's better than galaxy surveys to probe the larger scale structure in regimes in which you have like source confusion because they are very faint, or you don't have enough sources that you can detect. So that's why line intensity mapping is going to be good in this regime that I'm discussing for those redshifts or probing those very small masses that galaxy surveys don't have access to. I haven't discussed this because I'm not expert on that, but then if you go to reionization and cosmic dawn, the phenomenology is completely different, and then you have a lot of information there to probe models beyond of lambda cold dark matter, because, for example, the onset of the cosmic dawn is in the first galaxies that are formed, that are still very small, and in halos that are very light, and those are very sensitive when those galaxies form, are very sensitive to anything that happens at a smaller scale in the power spectrum. So if you have any suppression of the power spectrum or enhancement for whatever physical processes, you're going to be very sensitive to that. So then the sensitivity to new physics is much richer and diverse, and beyond the reach of like probing generally the large scale structure in the cosmic dawn and reionization. For after ionization is going to be, for cosmology, just getting where galaxy surveys struggle to get to.
Thanks a lot.
Paolo?
Thank you for your seminar. And my question is then since we have some information with JSUST of objects, say redshift 5, 15, let's say. So this new method, just to have one idea, it will be able to get a mass function of object, let's say at redshift 10, out down to which mass, for instance?
I can't tell you to the mass right now. It depends a lot on whatever astrophysical. It depends a lot on the line and the regime that you are looking at. One way to model this is this kind of, in a very phenomenological and naive way, assuming a relationship between the halo mass and the luminosity on the lines that you have information from. Depending on the line, you start having contributions from
Okay.
masses of 10 to the 8, 10 to the 9 for after reionization. For before reionization, you are sensitive indirectly up to case of 100 inverse megaparsec approximately.
Sorry, not to be rude, but so it doesn't help then in the main, let's say, issues that we have for galaxy formation at redshift 10. So, because you said you were very well, I mean, optimistic in this, no? But the main thing is to say, for instance, how many objects there are out there at redshift, let's say 10, and what is their mass? This is the main point for lambda CDM and variation lambda CDM. So all the rest, okay, is more complex. But you are telling that doesn't really is not a game changer on this method.
So at redshift 10, I think it's going to be, because it's going to be complementary to observations, for example, like JSWST, that are going to be very pencil beam observations. And here you're going to be able to, again, in a very indirect way, probe the population of ionizing sources that you may have.
Okay, thank you.
Can thank Jose again.
Thank you very much.